You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Image generation control refers to the suite of techniques that steer generative models toward producing intentional, structured, and safe visual outputs. Generative models, particularly diffusion and transformer-based architectures, have reached a point where they can create strikingly realistic or artistic images from text prompts alone. Yet without control, these outputs may be unpredictable, inconsistent, or even unsafe. Control mechanisms transform image generation from an exploratory art into a disciplined practice, where outcomes are not left entirely to chance but shaped by clear guidelines. The analogy is similar to photography. A camera may capture whatever passes before its lens, but with focus, framing, and filters, a photographer directs the image into a purposeful expression. In AI, control methods provide the equivalent of those tools, ensuring that the creative process is aligned with user intent, organizational needs, and ethical boundaries. Conditioning inputs are one of the primary tools for guiding image generation. In practice, conditioning means providing the model with additional signals beyond the basic prompt. These signals might be sketches, edge maps, semantic layouts, or reference images. For example, a designer can sketch a rough outline of a character and ask the system to render it in full detail, or a photographer can provide a portrait that the model uses as the basis for stylistic variations. Conditioning narrows the space of possibilities, making outputs more predictable and aligned with the initial vision. Without conditioning, text prompts alone may yield results that are surprising or inconsistent, since language is inherently ambiguous. By anchoring prompts with visual or structural guides, conditioning transforms open-ended creativity into directed design, giving users finer control over outcomes while still leveraging the generative power of the model. Text-to-image models are the backbone of modern generative imaging. These systems, often built on diffusion processes or transformer-based architectures, take textual descriptions and translate them into coherent visuals. Diffusion models work by progressively denoising random noise into structured images, guided by the semantic meaning of the input text. Transformer-based systems, by contrast, model image generation as a sequential prediction task, where visual tokens are generated in alignment with language. Both approaches rely on massive datasets of paired images and captions to learn how words correspond to visual features. For instance, when asked to generate, quote, "a lighthouse on a rocky coast during sunset," the model combines learned patterns of coastal landscapes, lighting conditions, and object relationships to create a plausible image. These models provide the raw generative capacity, while control mechanisms refine and shape their outputs into reliable, intentional designs. Editing capabilities extend these models beyond creation into modification. Techniques such as inpainting and outpainting allow users to alter specific regions of an image while keeping the rest intact. Inpainting can remove unwanted objects, replace them with alternatives, or correct flaws. Outpainting expands images beyond their original borders, filling in plausible backgrounds or extensions. For example, a user might upload a photo and ask the system to replace the sky with a sunset, or to expand the canvas to include more of the surrounding environment. Editing transforms generative models into tools not only for original creation, but also for refining and adapting existing content. This flexibility is particularly valuable in design workflows, where iteration and revision are constant. Editing also raises unique challenges, since alterations must blend seamlessly with existing content to avoid appearing artificial or misleading. Style control is another powerful dimension of image generation. Through carefully crafted prompts, users can guide models to render images in particular artistic genres, such as Impressionism, Cubism, or photorealism. Beyond art, style control can enforce consistency across a brand's marketing materials or unify the aesthetic of a series of illustrations. For example, a company may specify that all generated product mockups should use a flat, minimalistic design consistent with their corporate identity. Style control works by conditioning the model on stylistic cues, either explicitly through prompt engineering or implicitly through fine-tuning on targeted datasets. The result is not just images that represent content, but images that represent content in the desired manner. This capability broadens the creative reach of generative models, making them tools not only for visual storytelling but also for design coherence and identity expression. Safety levers are critical to ensuring that image generation remains responsible. Without safeguards, generative models can be misused to produce harmful, biased, or inappropriate content. Safety levers may include filters that block certain categories of prompts, classifiers that detect and prevent unsafe outputs, or moderation layers that review generated images before release. For instance, a platform may prevent requests that attempt to generate explicit or violent content, or it may blur sensitive regions before images are displayed. These safety systems operate in tandem with guardrails established during training, such as removing unsafe examples from datasets. The goal is to balance creativity with responsibility, ensuring that models empower users without exposing them to harm. Safety levers are not static. They evolve as new risks and misuse scenarios emerge, requiring continuous refinement and oversight to remain effective. Latent space guidance offers another dimension of control. Generative models operate within a latent space, a high-dimensional representation where visual concepts are encoded numerically. By adjusting positions within this space, users can nudge outputs toward desired features. For example, moving slightly along a dimension might change the lighting from day to night, or shift a face from smiling to neutral. Latent guidance provides fine-grained control without requiring explicit textual prompts. This technique is particularly useful for adjusting subtle details such as style, emotion, or atmosphere. It transforms the generative process from a one-shot command into an interactive exploration, where users can steer results iteratively. While powerful latent manipulation requires care, since small shifts can sometimes produce unpredictable results. Nonetheless, it represents one of the most flexible ways to guide image generation at a technical level. Consistency across multiple images is a persistent challenge in generative systems. When asked to generate a series of images of the same character, for example, models may vary details such as hairstyle, clothing, or facial features. Achieving consistency requires specialized approaches, such as conditioning on reference images, fine-tuning on specific characters, or using embedding techniques that fix key attributes. For applications like storytelling, product marketing, or simulation, consistency is essential. Users expect the same character or object to look recognizable across contexts. Inconsistent outputs erode trust and limit usability. Addressing this challenge remains an active area of research, with techniques such as identity-preserving embeddings and multi-image conditioning showing promise. Consistency transforms image generation from one-off novelty into a tool for sustained creative and professional use. The applications of image generation control in design are wide-ranging. Creative industries rely on these tools for prototyping, marketing, and content creation. A designer can generate multiple variations of a logo concept quickly, evaluate them, and refine the best options. Marketing teams can create campaign visuals tailored to different demographics, ensuring alignment with cultural expectations. Prototyping becomes faster when visual ideas can be explored at scale without committing time or money to manual rendering. In entertainment, controlled image generation supports concept art, storyboarding, and visual experimentation. The key advantage lies in accelerating the creative process, allowing human professionals to explore broader design spaces and focus their energy on refinement rather than initial generation. Beyond design, accessibility is another area where image generation proves valuable. For educational and training contexts, generated visuals can help illustrate complex ideas or create simulations for learners who benefit from visual reinforcement. For example, a science teacher could generate diagrams that show molecular structures or historical scenes for students without access to traditional illustrations. People with limited visual imagination can use generated images to explore concepts described in text, making abstract ideas more concrete. In training environments, generated images can create practice scenarios that are difficult or expensive to replicate in real life, such as medical conditions or emergency simulations. By making visualization accessible to more people, image generation enhances inclusion and broadens educational opportunity. Evaluating image outputs requires balancing multiple criteria. Quality refers to whether the image is aesthetically coherent and free from artifacts. Alignment measures whether the output matches the prompt or conditioning inputs faithfully. Safety evaluates whether the content adheres to ethical guidelines and avoids harmful material. These criteria are often in tension. Pushing for higher realism may increase the risk of inappropriate outputs, while strict safety filters may block legitimate creativity. Evaluations may involve both automated metrics and human judgment, since perception of image quality and meaning is subjective. By systematically measuring these factors, organizations ensure that image generation tools remain useful, reliable, and trustworthy. Transparent evaluation is also essential for building confidence in enterprise adoption, where mistakes can carry reputational or regulatory consequences. Bias in image generation remains a serious concern. Training data often reflects social inequalities, and models may reproduce these biases in their outputs. For example, prompts for professional roles may disproportionately generate images of men, while prompts for caregiving roles may favor women. Geographic or cultural biases can also appear, where wedding might default to Western imagery rather than global diversity. Such biases are not only technically problematic but also socially harmful, reinforcing stereotypes and marginalizing underrepresented groups. Addressing bias requires a combination of dataset curation, debiasing techniques, and ongoing monitoring of outputs. While complete elimination of bias may be impossible, responsible design aims to reduce its prevalence and make systems more inclusive. Recognizing and addressing bias is part of the broader ethical responsibility of deploying powerful generative models. Industrial controls highlight how enterprises adapt image generation for professional contexts. Consumer-facing systems may allow more open-ended creativity, but businesses require stricter guardrails to ensure brand safety and regulatory compliance. Enterprise tools often include pre-configured policies that block certain categories of outputs, enforce consistent style, or limit usage to approved workflows. For example, a financial institution may use image generation for marketing materials but require all outputs to pass compliance review. Industrial controls thus extend beyond technical capabilities to organizational governance, ensuring that generative models serve professional needs without introducing risk. These controls demonstrate how image generation must adapt as it moves from novelty applications into critical business infrastructure. As this first half concludes, it is clear that image generation control is not about restricting creativity, but about channeling it responsibly. Conditioning inputs, editing capabilities, style control, safety levers, latent guidance, and consistency techniques all work together to create systems that are not only powerful but also usable, reliable, and aligned with human goals. These tools transform generative models into practical instruments for design, accessibility, and enterprise use. They balance freedom with structure, ensuring that outputs are intentional rather than accidental. The next stage of the discussion will explore how these methods extend into more advanced transformations, such as image-to-image editing, reference conditioning, and cross-domain applications, showing that control is not only about safety, but also about unlocking broader opportunities in simulation, training, and creativity. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Image-to-image transformation is one of the most versatile aspects of controlled generation because it allows users to create new images by modifying or expanding upon an existing one. Instead of beginning with a blank slate, the system is guided by a source image which can be altered to introduce variations or refinements. For example, a designer might take a product photo and generate different color schemes, lighting conditions, or background environments. Similarly, an artist might input a rough sketch and transform it into a fully realized painting in a chosen style. This capability makes image generation not only a tool for creation, but also a tool for iteration, enabling rapid prototyping and experimentation. Image-to-image workflows are particularly powerful in professional contexts where maintaining a base level of consistency is important while still allowing for creative exploration. The result is a fusion of originality and coherence, ensuring that outputs stay grounded while still offering diversity. Reference image conditioning expands this idea further by anchoring generation to specific visual examples. Instead of working from only text prompts, users provide photos or illustrations that establish the subject, pose, or composition. The model then uses these references to produce variations that maintain key elements while introducing stylistic or contextual changes. For example, a fashion retailer may upload a model photograph and generate outfits in different colors or patterns, while still preserving the body shape and pose. In animation or character design, reference conditioning ensures that the same character remains recognizable across different scenarios or environments. This technique resolves one of the persistent challenges in generative systems: consistency across multiple outputs. By tying generations back to a reference, the system maintains identity and continuity, making it more practical for enterprise and creative industries where brand or character fidelity is critical. Control networks, such as ControlNet, represent a significant breakthrough in fine-grained generation. These models augment diffusion processes by providing structural guidance from inputs like edge maps, depth maps, or segmentation masks. For example, by feeding a depth map into a control network, users can ensure that generated content respects the spatial arrangement of objects in a scene. This adds a layer of precision, allowing outputs to align closely with user intent. Control networks effectively bridge the gap between free-form creativity and structured design, making it possible to generate outputs that are not only aesthetically pleasing, but also technically accurate. They are especially valuable in fields like architecture, robotics, and manufacturing, where spatial relationships matter. Control networks turn generative models into tools that combine artistry with engineering, extending their usefulness into domains where precision is non-negotiable. Simulation is one of the emerging applications of controlled image generation. Robotics teams, for instance, require vast numbers of training images that depict environments, objects, and scenarios their robots might encounter. Generative systems can produce synthetic data tailored to these needs, filling in gaps where real-world data is scarce or expensive to collect. Similarly, training environments for autonomous vehicles can be enhanced with generated images of traffic conditions, weather variations, or rare but critical edge cases. In other fields, simulations help train professionals in scenarios that cannot be easily recreated physically, such as medical procedures or emergency responses. By controlling generation with precision, organizations can ensure that simulations are not random but purposeful, aligned with learning goals. This shows how image generation can move beyond creativity into practical engineering, creating worlds that prepare machines and humans for the complexities of reality. Yet with these powerful editing and simulation capabilities come risks related to misinformation and authenticity. When images can be modified seamlessly, distinguishing between genuine and altered content becomes difficult. A benign use case, such as replacing a cloudy sky with a sunny one in a travel brochure, may look visually similar to a malicious use case, such as altering a news photo to mislead the public. This duality makes editing a double-edged sword. On one hand, it empowers creativity and efficiency. On the other, it introduces opportunities for manipulation. The challenge is not only technical but social. How can societies retain trust in visual media when alteration is ubiquitous? Addressing this requires a combination of technical safeguards, policy frameworks, and public literacy. Users and organizations alike must recognize that the ability to edit does not absolve responsibility for truthfulness and authenticity. Watermarking is one of the most promising safeguards for ensuring provenance and verification of generated images. By embedding invisible signals into outputs, watermarking makes it possible to trace whether an image was created or modified by a generative system. These signals can be robust against manipulation, surviving, resizing, or compression while remaining detectable through specialized tools. For example, a media company might use watermarking to label generated illustrations in order to distinguish them from human-created art. Governments and regulators may require watermarking for generated political or news imagery to prevent misinformation. While watermarking is not foolproof, it establishes a baseline of accountability, allowing organizations to demonstrate transparency. It also gives users confidence that they can verify authenticity when needed. As generative systems become more widespread, watermarking will likely become a standard feature, balancing creative freedom with societal trust. Regulatory considerations are closely linked to watermarking and authenticity. As image generation becomes a mainstream capability, governments are beginning to debate when and how generated images should be disclosed. For example, advertising regulators may require companies to disclose when marketing visuals are synthetic. In journalism, disclosure may become mandatory to prevent audiences from mistaking generated imagery for authentic documentation. In entertainment, disclosure may protect against misrepresentation of performers. Regulations will vary by industry and jurisdiction, but the underlying principle is consistent. Users and consumers deserve to know whether what they are seeing is real or generated. Organizations that embrace transparent disclosure may not only meet regulatory requirements, but also build stronger trust with their audiences. Proactively integrating disclosure mechanisms shows responsibility and foresight in a rapidly evolving landscape. Scalability is a practical challenge for enterprises that rely on image generation at industrial scale. Generating one or two images may seem trivial, but producing thousands or millions for large campaigns, catalogs, or training datasets requires significant optimization. Batch generation pipelines must manage compute resources efficiently, balancing speed with quality. Caching intermediate outputs, reusing embeddings, and applying distributed computing strategies all help scale generation. Cost is also a factor, as each generated image consumes computation and storage. Without careful design, scaling generative systems can become prohibitively expensive. Organizations must therefore plan workflows that are both technically efficient and financially sustainable. Scalability is not just about volume. It is about creating repeatable, optimized processes that ensure consistent results across massive output sets. User interface integration is another area where controlled image generation reaches real-world adoption. While researchers may interact with models through code, most users require accessible software tools. Modern design platforms integrate generative features directly into familiar interfaces, allowing non-experts to use inpainting, style control, or conditioning without technical knowledge. For example, a graphic design program may include a Fill with AI option that enables users to remove or replace objects in a photo with a single click. These integrations democratize access, expanding the reach of generative systems beyond technical experts into mainstream creative industries. The design of interfaces also influences adoption. Tools that feel intuitive and seamless encourage experimentation, while complex or opaque controls may deter users. Making control features accessible ensures that the benefits of generative AI are widely shared. Research continues to advance the frontier of controllable diffusion and multimodal editing. New algorithms allow for finer granularity of control, such as adjusting lighting, composition, or object attributes with greater precision. Multimodal editing integrates not only images and text, but also other inputs like sketches, gestures, or even spoken instructions. These innovations expand the ways users can guide generation, making it more natural and interactive. For example, an artist might hum a melody that inspires a visual style, or a teacher might sketch a diagram that the system turns into a polished illustration. The goal is to reduce the gap between human intention and machine execution, enabling more fluid collaboration. Research in this area underscores the trajectory of generative AI, from static prompts to rich multimodal dialogues that capture creativity in all its forms. Ethical dimensions remain central as these technologies evolve. Systems that give users fine control also carry the risk of misuse. For example, tools that allow realistic editing of faces or documents can be exploited for fraud or harassment. Balancing creativity with responsibility requires embedding safeguards that prevent harmful uses without unduly restricting legitimate expression. This balance is not easy. Too much restriction stifles innovation, while too little oversight enables abuse. Ethical design involves transparency, user education, and accountability mechanisms. It also requires a cultural shift, where creators and organizations recognize that responsibility is as much a part of the creative process as freedom. Ethical dimensions remind us that image generation control is not just a technical problem but a societal one, requiring shared values and collective oversight. Cross-domain opportunities illustrate the broad impact of controlled image generation. In healthcare, it can be used to create training images for rare conditions, helping medical professionals recognize symptoms more effectively. In manufacturing, it can generate visual simulations of assembly processes, supporting worker training and safety. In entertainment, it enables rapid prototyping of characters, environments, and special effects. Each of these applications relies on control to ensure relevance, accuracy, and trustworthiness. Without control, generated outputs may be beautiful but irrelevant. With control, they become valuable assets aligned with organizational goals. Cross-domain adoption shows that image generation is not confined to art or marketing. It is becoming a general-purpose capability that supports productivity, learning, and innovation across industries. Security implications arise from the potential misuse of generative systems. Malicious actors may attempt to create misleading images for disinformation, phishing, or impersonation. Without safeguards, these tools can amplify existing threats in cybersecurity and social trust. Organizations must therefore embed security into the very design of generative platforms. This includes monitoring for malicious usage patterns, applying content filters, and ensuring traceability of outputs. Security also requires user education. People must be aware of the risks of synthetic media and trained to verify authenticity. Just as cybersecurity evolved into a central concern of the digital age, securing generative systems will be a defining challenge of the AI era. Addressing these implications early ensures that innovation remains a force for good rather than a tool for harm. The future outlook for image generation control is one of increasing fidelity, flexibility, and responsibility. Models will continue to improve in realism, producing outputs indistinguishable from real photographs or sophisticated art. Control mechanisms will grow more refined, allowing users to adjust every aspect of generation from composition to emotion. Safety levers, watermarking, and regulatory frameworks will evolve in parallel, ensuring accountability. As models gain fidelity, the need for strong governance will only grow, since the risks of misuse increase with realism. Nonetheless, the trajectory points towards systems that empower creativity, support industries, and democratize access to visual expression. The challenge is ensuring that these benefits are realized responsibly, with controls that balance freedom and safety. As we transition to the next discussion, it is clear that image generation is not the only modality where control matters. Speech generation pipelines raise similar challenges of conditioning, style, and safety. Just as visuals must be generated responsibly, so too must audio, where risks of impersonation or harmful content carry serious implications. By examining how speech generation applies similar principles, we can see how generative control extends across modalities, uniting vision, language, and sound under the same imperative: creativity guided by responsibility. Image generation control thus represents both the promise and the responsibility of advanced AI. Through conditioning, editing, style guidance, and safety mechanisms, these systems empower users to create intentional, meaningful, and responsible visual outputs. They offer opportunities across design, accessibility, education, and industry, while also demanding safeguards against misuse. The balance lies in harnessing creativity without sacrificing trust. As these models grow in fidelity, the need for control will only intensify. By embedding safety, transparency, and responsibility alongside power, we can ensure that generative imagery remains a force for innovation rather than division, enriching human expression while protecting the integrity of shared visual reality. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.